In the unending silence of the cosmos, there are stories. They are not written in words, nor are they carried on sound. These sagas are inscribed in the ancient light of distant suns. They are whispered in the spectral fingerprints of molecules drifting through cradles of dust and gas a million lifetimes away. For most of human history, we could only look up and wonder our eyes, seeing only the brilliant, enigmatic points of stellar fire. The universe was a silent film, beautiful but mute. Now we have learned to listen. Our ears are not made of flesh, but of polished gold mirrors unfurled in the freezing vacuum of space, a million miles from home. The James Webb Space Telescope is more than a machine of glass and wire. It is a time-traveling ear, an instrument of cosmic archaeology built to capture the faintest, oldest murmurs of creation. Its gaze was recently directed toward a place of profound significance, a location far beyond the familiar spiral arms of our own Milky Way. It turned its attention to the large Magellanic Cloud, a satellite galaxy, a celestial island of billions of stars, forever tethered to our own. This shimmering neighbor, visible only from the southern hemisphere, is a cosmic laboratory, a realm with a different chemical history. It is poorer in the heavy elements forged in the hearts of ancient stars, a more primitive environment, a glimpse into the universe's own youth. Within this companion galaxy, in a turbulent ocean of nebulosity, lies a stellar nursery, a place where new suns are being born. The target was a specific protostar, an infant sun named IRAS 05328-6827, still swaddled in the dense opaque cocoon of its natal cloud. No optical telescope could ever pierce this thick veil of cosmic dust. But Webb's infrared vision cuts through the haze like a phantom, revealing the secret chemistry happening deep within the stellar womb. Scientists were not just looking for a new star. They were searching for the ingredients of worlds yet to be made, the raw materials that might one day coalesce into planets, moons, and perhaps life. Data translated from photons into numbers streamed across the void. It arrived at Earth as a cascade of silent information, a spectral graph filled with peaks and troughs, a barcode of the star's environment. Each peak, each dip is the signature of a specific molecule vibrating, rotating, and absorbing light in its own unique way. The team of astronomers saw the familiar signatures first. They found the deep absorption lines of water ice, the universal solvent. They identified the presence of carbon monoxide and carbon dioxide, simple but essential building blocks for more intricate structures. There was methane, ammonia, the fundamental components of planetary atmospheres, but as they sifted through the noise, a fainter, more complex signal emerged. It was a delicate pattern, a subtle arrangement of spectral lines that did not belong to any of the simple molecules they expected to find. This was something different, something more evolved. The computer models churned, cross-referencing vast libraries of molecular fingerprints against the ghost in the machine. And then, the confirmation arrived, an astonishing revelation that rippled through the global astronomical community. Hiding in the frigid deep freeze around this embryonic star 160,000 light-years from Earth was the unmistakable signature of acetic acid ice, vinegar. The sharp, pungent essence of salad dressing and pickling jars found frozen solid in a cloud of gas at the edge of another galaxy. It is a discovery so profound and so mundane it borders on the surreal. To comprehend its significance, we must first step back and reconsider the very nature of the space between the stars. We tend to imagine the void as a sterile, empty place, a perfect vacuum of absolute nothingness. This perception could not be more mistaken. Interstellar space is in reality a colossal chemical factory, a slow-motion laboratory operating on scales of time and distance that dwarf our terrestrial comprehension. Imagine a kitchen, the largest kitchen imaginable, stretching for light years. The countertops of this kitchen are the microscopic surfaces of dust grains, tiny specks of silicate and carbon, colder than anything on Earth. These frozen motes are the mixing bowls for cosmic creation. Floating through this kitchen are the simplest ingredients, individual atoms of hydrogen, oxygen, carbon, and nitrogen, forged in the hearts of stars that died billions of years ago. The oven, the energy source that drives the reactions, is the harsh, unfiltered light of distant stars, a relentless bath of ultraviolet radiation. For eons in this impossibly cold and vast culinary expanse, a patient and methodical process has been unfolding. Atoms one by one stick to the frozen surfaces of the dust grains. They are like minuscule specks of flour and sugar settling on a chilled plate. Over millions of years, this dusting of atoms builds up. The intense cold holds them in place, while the occasional zap of a UV photon provides just enough energy to break their bonds and rearrange them. First, the simplest recipes are followed. 2 hydrogen atoms find an oxygen atom, forming the frost of water ice. A carbon atom links with an oxygen atom, creating carbon monoxide. These are the fundamental staples, the water and flour of the cosmic pantry. For decades, astronomers have been proficient at detecting these simple molecules. They have found them throughout our own Milky Way, confirming that the basic ingredients for worlds like ours are disconcertingly common. But the discovery of acetic acid is something else entirely. This is not flour. This is not water. This is a complex sauce, a pre-mixed marinade. Acetic acid, with its chemical formula CH3COOH, is a member of a special class known as complex organic molecules. It contains 8 atoms bound together in a sophisticated structure. It possesses what chemists call a carboxyl group, a specific arrangement of carbon, oxygen, and hydrogen that is a foundational component of every single amino acid, the building blocks of proteins. Finding this molecule is like walking into that immense cosmic kitchen and discovering that the universe isn't just stocking raw ingredients. It has already started preparing the dough. It's following a recipe that leads toward the chemistry of life. The presence of vinegar ice tells us that the universe, even in chemically primitive galaxies, is capable of assembling molecules that are direct precursors to biological systems. This single detection is a powerful testament to a concept that was once the domain of science fiction and philosophy, the idea that the universe is fundamentally primed for life. To appreciate the journey that led to this moment, we must travel back through the centuries to a time when the stars were merely divine mysteries. The ancient Greeks looked at the heavens and saw gods and heroes, their imaginations painting pictures on a canvas of inaccessible light. They could ask what the stars were, but they had no means to answer. The first revolution came with the telescope in the 17th century. Galileo Galilei pointed his crude instrument skyward and shattered the illusion of celestial perfection. He saw mountains on the moon, witnessed moons orbiting Jupiter, and resolved the Milky Way into a countless multitude of individual stars. The heavens were a physical place, not just a divine tapestry, yet the fundamental question remained. What were these places made of? The answer would come not from seeing farther, but from seeing differently. In the early 19th century, a German optician named Joseph von Fraunhofer was experimenting with prisms splitting sunlight into its rainbow spectrum. He noticed something peculiar. The sun's spectrum was not continuous. It was crossed by hundreds of dark, thin lines, a celestial barcode. He meticulously mapped these lines, but their meaning remained a mystery. Decades later, Gustav Kirchhoff and Robert Bunsen made the critical connection. They discovered that when they burned different chemical elements in a flame, each element emitted light at specific unique colors, a bright line spectrum. Crucially, they realized that a cool gas would absorb those very same colors from light passing through it, creating a dark line spectrum. The puzzle pieces snapped into place with a thunderous intellectual crash. Fraunhofer's dark lines in the sun's spectrum were absorption lines. They were the chemical fingerprints of elements in the sun's cooler outer atmosphere. Humanity, for the first time, could perform a chemical analysis of a star. We learned that the sun was made of hydrogen, helium, sodium, iron, the very same elements found here on our own planet. This was the birth of astrophysics, the moment we understood that we were not separate from the cosmos, but an integral part of it. As Carl Sagan would so elegantly phrase it more than a century later, we are made of star stuff. The 20th century expanded this new sense, this spectroscopic vision. Radio telescopes allowed us to listen to the cold universe, to the regions between the stars where no visible light was emitted. In these dark, frigid clouds, astronomers began finding the signatures of simple molecules one after another, a growing inventory of the galaxy's chemical wealth. But these discoveries were all confined to our own cosmic backyard. They were all within the Milky Way, our home galaxy, an environment rich in the recycled elements of countless generations of stellar birth and death. A critical question lingered in the minds of astrobiologists. Is this rich life-sponsoring chemistry a fluke? Is it a unique consequence of the Milky Way's specific age and evolution? Or is the universe's tendency to create complexity a universal law, a fundamental principle that operates everywhere, in all galaxies at all times? Answering this question required a technological leap of staggering proportions. It required an observatory so sensitive it could detect the faint infrared glow of molecules in another galaxy across a chasm of 160,000 years of light travel. It required the James Webb Space Telescope. The discovery of acetic acid in the Large Magellanic Cloud is the first resounding piece of evidence that the cosmic recipe book is not exclusive to our corner of the universe. The LMC is a different kind of galactic environment. Its stars and gas clouds have a lower metallicity, an astronomical term for the abundance of elements heavier than hydrogen and helium. This means there is simply less raw carbon, oxygen, and nitrogen available to build complex molecules compared to a typical star-forming region in our galaxy. Finding not just simple molecules but a sophisticated one like acetic acid in such a metal-poor environment is therefore profoundly significant. It suggests that the chemical pathways to complexity are robust and efficient. They can operate successfully even when the starting ingredients are scarcer. The universe, it seems, is exceptionally good at making the precursors to life. It is a tenacious and persistent chemist. This single finding dramatically expands the potential real estate for life in the cosmos. It tells us that we do not need to search only for galaxies identical to our own. The seeds of biology might be sown in a much wider variety of galactic soils than we ever dared to imagine. The discovery also offers a tantalizing glimpse into our own deep past. 4.5 billion years ago, our own sun was a protostar, shrouded in a cloud of gas and ice, much like the one Webb observed. That primordial cloud was seeded with the same kinds of molecules: water, methane, and very likely acetic acid and other complex organics. These molecules, frozen onto dust grains, became incorporated into the asteroids and comets that formed in the nascent solar system. For For hundreds of millions of years, these cosmic icebergs, these celestial delivery trucks, bombarded the young, barren Earth. Each impact was a catastrophe of unimaginable violence, but each impact also delivered a precious cargo water to fill the oceans and the complex organic molecules that would become the feedstock for life. The vinegar ice detected in that distant protostellar cloud is not merely a chemical curiosity. We are looking at a snapshot of the very process that may have seeded our own planet with the components necessary for biology. We are witnessing across the gulf of intergalactic space a replay of the first chapter of our own origin story. This deepens the connection we feel to the cosmos. The processes are not alien, they are universal. The story is not just ours, it belongs to the stars. But this discovery also pushes us towards even more profound, more unsettling questions. If the ingredients are everywhere, if the recipe is universal, and if the ovens of stellar nurseries are constantly baking, then where is everybody? This is the famous paradox articulated by the physicist Enrico Fermi, the apparent contradiction between the high probability of extraterrestrial life and the complete lack of any evidence for it. The detection of extragalactic acetic acid sharpens the horns of this dilemma. It strengthens the argument that the chemical precursors for life are not the bottleneck. The universe is clearly adept at this stage of the process. So, if life's starting materials are common, the bottleneck must lie elsewhere. Perhaps the leap from complex chemistry to simple replicating biology is an event of truly astronomical rarity, a fluke that has happened only once. Or maybe life arises frequently, but intelligence is the rare phenomenon. Or in a more somber reflection, perhaps intelligent life inevitably develops the means of its own destruction before it can ever reach out across the interstellar distances. We do not have the answers. But with each discovery like this one, we refine the questions. We move from pure speculation towards empirically grounded inquiry. We are charting the vast unknown territory between chemistry and biology. And the search is accelerating. The James Webb Space Telescope is just the beginning of a new era. Future observatories, both on the ground and in space, will be even more powerful. They will be designed not just to find these frozen ingredients in stellar nurseries, but to search for the consequences of them on mature planets. The next great quest is to analyze the atmospheres of exoplanets, Earth-sized worlds orbiting distant stars. We will hunt for biosignatures, telltale chemical imbalances that could only be explained by the presence of a thriving global biosphere. We will search for the atmospheric fingerprints of oxygen and methane existing together in a delicate disequilibrium maintained by life. We will look for the waste products of alien metabolisms, the subtle exhalations of a living world. It is entirely possible that within the lifetime of people watching this now, we will point a telescope at a pale blue dot orbiting another sun and find definitive, incontrovertible evidence of life. That moment, if it comes, will represent a turning point in the history of our species, a fundamental recalibration of our place in the universe. It will be the culmination of a journey that began with our ancestors looking up at the night sky in fearful wonder. Until then, we continue to listen to decipher the stories told by light. We return our gaze to that infant star in the large Magellanic Cloud 160,000 light-years away. The cloud that surrounds it is a place of immense potential. For now, it is a frigid, dark and chaotic environment, but in a few million years the protostar will ignite into a true sun. Its light and heat will push back the surrounding gas and dust, revealing the family of young planets that have formed in its orbit. Some will be gas giants, others barren rocks. But perhaps one will orbit within the habitable zone, the Goldilocks region, where temperatures are just right for liquid water to exist on its surface. And that world will have been born with a precious inheritance. It will be seeded from the very beginning with water and with the complex organic molecules like acetic acid that we have now detected. It will have all the necessary ingredients for its own genesis. What happens next on that world is a story yet to be written. Will the chemistry lie dormant for eternity in sterile oceans, or will some spark, some chance combination of molecules in a primordial soup ignite the chain reaction of replication and evolution? Will that world, billions of years from now, develop its own life, its own ecosystems, its own consciousness? Will beings evolve there who will one day build their own telescopes and look out across the intergalactic void towards a faint, unremarkable spiral galaxy they call the Milky Way? We cannot know, but what we do know with more certainty now than ever before is that the universe is not a barren, empty stage. It is a fertile garden, constantly sowing the seeds of possibility. The discovery of vinegar ice in another galaxy is more than a data point. It is a message carried on ancient light across an ocean of time and space. It tells us that the laws of chemistry and physics are not random. They are biased in favor of complexity, in favor of structure, and perhaps in favor of life itself. The scent of vinegar, a faint chemical whisper from a stellar nursery, reminds us that we are not isolated miracles. We are the natural, perhaps even inevitable products of a creative cosmos. And in that vast, silent darkness, we may not be as alone as we think.